for the introduction. My name is Joonseok Lee. Currently, I'm working for Google. This work was done in Microsoft Research when I was on internship last year. So what is contextual entity exploration problem? This lady is reading an article on her tablet. And the article is about some historical events which occurred during the American Revolutionary War. So while she was reading this article, she got interested in knowing more about this person, Silas Dean. So what she can usually do is connecting to the Google or Bing web search engine, then type Silas Dean, then it will give some pages relevant to those queries. So that works, but it's limited. First of all, she needs to switch to another application, which is distracting. And also, more importantly, the search engine does not know why she is interested in this particular person. So in other words, web search engines will lose the context of this text that she was reading. So if we can do this interaction within the application directly in this application, then we are able to take advantage of the context here. So what we want is when she clicks and do some direct interaction within this application, we want to show some list of recommendations such as Silas Dean Wikipedia page describing about his life, as well as some contextually relevant pages such as American Revolutionary War or Benjamin Franklin, who was a colleague diplomat of Silas Dean. So this is an example of in real production. So in Microsoft Word Online, MS launched a new feature called Insights. So when we are writing something, we can search some words or phrase there. Then it shows some relevant information on the right side. So how can we implement this idea? So in literature, most works in this contextual exploration problem was implemented by query rewriting approaches. So when the user clicks or interacts with the context, it extracts the term and finds out that word. And also it extracts some context words, some keywords like Ticonderoga or Connecticut or Benedict Arnold here. And it constructs by using some of those subset of the keywords it extracted. So for example, Silas Dean, rank only Connecticut, and rank only Ticonderoga. And this query is sent to the search engine, and it receives the list of the pages. Then it applies some post-filtering to finally show to the users. This approach was working well, but it's still a little bit limited in some sense. Because it's using the web search engine with the keyword search, it can be extracting only the syntactically related words. Because, for example, Silas Dean and Ticonderoga. But, for example, Benjamin Franklin is not shown any of this context, so it cannot relate it just based on the semantics. So how can we leverage semantics and how they are actually related in the scene behind? So we propose using knowledge base or knowledge graph to find out semantically relevant pages as well as the syntactically relevant pages. So we match these keywords to the entities in the knowledge base. Then we can use the relationship between those entities from the knowledge graph. So this is the summary of the problem definition. The contextual entity exploration system gets two inputs, the user selection and the context. That's the text nearby the user selection. It may refer to the knowledge base. In our case, we use the Wikipedia graph to generate a list of recommendations up to 10 or some other K. So from now on, I'll detail the system we built. So we start with constructing a focused subgraph. Focused subgraph is a subgraph of the entire Wikipedia graph containing the nodes and edges which are relevant to the problem instance, in our case, the Silas Dean example. So we start with finding out the perfectly matching starting page called Silas Dean. we can use any entity linking method for this purpose. We use the in-house Microsoft one, but any other entity linking can be used. And we do the same thing for the context nodes, such as Green Mountain Boys, which is the name of troop participated in the capturing the Fort Ticonderoga, and Fort Ticonderoga or Connecticut, and some others. The next step is extracting some nodes which are semantically relevant to this particular example. For this, we extracted all the nodes which can be reachable by up to k hops from either user selection or from context nodes. In this example, I just showed by one hop some subset of the examples, but in real our experiment, we used 2 or 3 hops. And finally, we connect all of these existing nodes using the existing edges from the Wikipedia knowledge graph. So this is the focus subgraph for this particular problem instance. Our goal is retrieving 2 different types of relevant nodes. First type is Benjamin Franklin type. So recall that the article is about capturing the Fort Ticonderoga, some particular historical event. And Benjamin Franklin is a colleague of Silas Dean, but he did not participate in that historical event. But because the query itself is Silas Dean, Benjamin Franklin might be interesting as well to the user. So we want to find out some semantically relevant pages such as Arthur Lee or John Adams or Benjamin Franklin. Another type is American Revolutionary War type, which is connecting user selection Silas Dean to the context nodes such as Green Mountain Boys or Fort Ticonderoga. So these nodes are relevant to both the context as well as the user selection. So how can you find out these pages? We have 2 different subcomponents, 2 scoring methods. The first one is personalized random walk, which is most widely used in retrieving knowledge graphs. So random walk or personalized random walk computes the probability that each user can be staying in each node in a state manner. So we treated Silas Dean or the user selection node specially by giving some non-zero probability that we can jump from any other nodes to the first page. This actually simulates the user behavior because user starts from the perfectly matching page, then she can jump to any other page by the link, clicking the link from the page. And at some point, when she feels that this is no longer relevant to what she's interested in, then she might come back to the Silas Dean page and continues. So this method was useful to find out semantically relevant pages, which is located nearby the Silas Dean. But it's not enough for retrieving the pages connecting the context and user selection. So in this example, you can see that the context nodes were ignored by this method. So we need another approach to find out the nodes connecting these context nodes and user selection. How can you do that? We define a new concept, context selection betweenness, which retrieves the nodes that play an important role, connecting the user selection and the context nodes. We borrow the idea from the betweenness centrality, which is defined as the number of shortest paths from all vertices to all others that pass through that node. So intuitively speaking, this measures how much this particular node is playing an important role, connecting subcomponents of the graphs in terms of the shortest paths. In our case, we do not need to care about all the shortest paths from all vertices to all others, but what we are interested in is the shortest path connecting each context node and the user selection. So we just modify the summation part, and we can borrow the idea of betweenness centrality. Here's an illustration on our focus subgraph. We have 3 context nodes. The first one is Green Mountain Boys, and here's the shortest path to Silas Dean. And each of the nodes on that shortest path receives a score of 1/3 because we have 3 context nodes. The second one is for Ticonderoga. We also find American Revolutionary War is on that way, so it receives another 1/3 of the score. For the last one, Connecticut, we have a direct pass to Celestine, so only the node Connecticut receives the 1/3 of the score. And Celestine House is not in the shortest pass, so it does not be credited. So using these two scoring methods, we combine them, and we finally generate a list of the recommendations. For the details of the, how to combine those scores, please come to my poster. I will skip that for limited time. So here I will explain about the evaluation using the crowdsourcing. We used the 2,600 textbooks from Wikibooks for the corpora. And for the user selection, we asked to the crowd worker to choose the phrase or terms they are interested to know more about. So this is actually simulating how actually users are interested in. And for the evaluating our recommended pages, we also asked to the crowd workers to evaluate how much this recommended page is relevant to the problem instance. This was quite large scale because we have like 145,000 labels. So this is a screenshot for the user evaluation. So on the left side, we are showing the context and the user selection. In this case, it was a Bitcoin. And we recommended a page cryptocurrency. So the user or the crowd worker is supposed to read both of these two and answer how much it was useful or not on the bottom side. So this is the experimental result. We compared against several baselines, and we evaluated with mean average precision at k from 2 to 8 with the k. On the leftmost figure, our system Lewis was compared against 4 baselines, normalized Wikipedia distance, and the Leibniz, which is our previous system, using the syntactic relationships. And search engine, we used Bing as a baseline, and relevance feedback method. As we can see, Lewis is outperforming all the other 4 at all levels of case. The second, in the middle graph, we are comparing against our subcomponents. When we use only the CSV score or the random score, we see that they are underperforming than the entire system, which means both CSV and random scores are playing their own role, and without each other, it's performing worse than the entire system. So they are actually generating quite non-overlapping pages, and they are compensating to each other. And the rightmost figure, we are showing the upper bound of the performance if we have an oracle for the entity linking. Recall that we are using the entity linking method to get the first page, and we use the Microsoft in-house entity linker. You can imagine that it will not be perfect. So suppose we have the perfect entity linker, then we can achieve this level. Okay, this is the list of the recommendations by our system for the Celestine example. So we decompose the score between the CSV score and random score. And you see that several pages like Benjamin Franklin, Arthur Lee, or Thomas Jefferson, they were retrieved mainly because of the random scores. They are semantically relevant to Celestine, but not quite relevant to the context. But still, they're recommendable. And the other pages like Continental Congress or Continental Army or Capture of Fort Ticonderoga, these are having quite high CSV score. So they are recommended because they are connecting the context and the user selection. Finally, I have another example. So this is an article about pronunciation of the Greek word Ulysses. And the user is interested in knowing more about Oxford English Dictionary. So when you use the entity linking, we found perfectly matching page from the Wikipedia. And from our previous system called Leibniz, it's just based on the web search. it found some syntactically relevant pages such as New Oxford American Dictionary or Concise Oxford English Dictionary. Our system retrieved several pages, mainly based on the random walk, such as Greek language. Because there's no word Greek or Greece in this article, but it's talking about pronunciation of Greek word. So it was quite relevant page. And for the context selection betweenness, we found received pronunciation, which is standard English pronunciation in Britain. So because it's talking about Oxford English Dictionary, that was quite relevant recommendations. Okay, here's the summary of today's talk. I introduced the contextual entity exploration problem, and I proposed the knowledge graph-based solution, which incorporated semantic signals as well as the context-relevant retrievers. And we showed the evaluation results with IR measures, which was performing quite well. And we also showed the crowdsourced evaluations. So tonight I have a poster session, so if you're interested in more about this, please come to my poster. Thank you.
Questions? Yeah. So you're now at Google, and Google has their own knowledge graph.
Yep.
What was the thing that surprised you most when you went to Google that you didn't expect from your research?
I'm not sure how to answer because currently I'm working in the YouTube department in Google, and I really recently joined, so I actually have no idea about what's going on in Google in this part. So, yeah.
Can you go back to the results? So the mean average precision, main presumption, the absolute number of the mean average precision, is that from a user study acceptability perspective?
Yes, right.
Is that acceptable? Is that good?
Yeah, we asked users to decide three of these options. The first one is perfectly matching. Second one is quite relevant. It's okay. And the last one is not relevant. And the crowd workers were harsher than we expected. So they usually give very low scores, partially because the task itself is very complex. They have to read all of those contexts and also read this page. And to answer the relevance between those two, it requires some knowledge to connect those two. So most of them actually didn't understand what's going on there, and sometimes they just give their lowest score. So yeah, that was the extra limitation of this crowdsource-based working.
I know the knowledge base, the construction of the knowledge base is very, very hard. So could you give me some technology that help us construct a better knowledge base?
The entire knowledge base?
Yeah, knowledge base.
Can you repeat the question for the recording?
Okay, yeah, this question is about how can we build the entire knowledge base in a better manner. Okay, yeah, that's a good question. We didn't think about that because we just assumed that the knowledge base itself is given. We use the knowledge graph from Wikipedia, or we can also use Freebase, but that's maybe another research direction that we can directly improve itself. So yeah, we can discuss it about that later. Yeah. Mm-hmm. Yeah.
So I wonder what is the turnaround time for your crowdsource-based evaluation?
Okay. Yeah, so she asked about the turnaround time for this evaluation. I used 500 examples, and to load and pre-process all of these knowledge graph, it took like 30 minutes. And after that, it's like constant time, like less than 10 minutes for 500 cases. The crowdsourcing. As I remember, it's like 2 or 3 days. We asked to 10 crowd workers for each instance, and we also applied some post-processing by detecting some random checkers. So yeah, overall we took like 48 hours, something. Mm-hmm.
Is that a general way to do it in Google, or is
It was in Microsoft.
it Microsoft?
Yeah.
Does Google will ship this technology in this product?
Oh, yeah, I'd like to mention that this was the work in Microsoft Research, and they were actually using this technology to incorporate in Microsoft Words as a name of insights. So I showed in the previous slides. Yeah. This.
Cool.
Yeah.
Sounds good. Thank you. Thank
Okay.
you so much.
Thank you.